Hello everyone. In this lecture we will cover the very famous active filter circuitry using op-amp. So what is filter? The very basic in electronic circuit and widely used in communication. So this filter is a electronic circuit, okay, which is basically a frequency selective circuit. Okay, so frequency selective circuit that passes the, or we can write that passes the specified band of frequencies, okay, and attenuates the rest, or we can say the other frequencies. Okay, so frequency selective circuit. Okay, this frequency selective circuit may be of low pass filter, okay, maybe high pass, band pass filter, band stop, and all pass. So in this video we will try to cover the only low pass filters. Okay, so actually in low pass filter we can pass a specified band of frequency. So I am just showing you the frequency response of a low pass filter, then we will discuss the circuit. Okay, so this one is this is your vertical axis, y axis is your gain in dB and frequency in hertz or kilohertz. Okay, so I am writing in hertz. This one is a 0 dB and minus. Okay, so this one is our pass band and the another one is your stop band. So in between 0 to fH, in between your 0 to fH, okay, is our pass band, and this region, the yellow one, is your pass band. Okay, this one, and the another one is our stop band. So in low pass filter, if for the time being I am considering this fH is equal to 100 hertz. Okay, so if we have any electronic filter circuit, some filter circuit, okay, this one is your input. So if we are giving an input having frequency 50 hertz, okay, It's a low pass filter circuit. Okay, so it will pass that 50 hertz. Okay, but if you are giving a frequency of signal having frequency more than 50 hertz, for example, I am giving this one, the green one, having frequency 110, so it will not pass the signal. Okay, so we are not getting the output will be 0, no output, because this circuit can pass up to 100 hertz. Okay, above this 100 hertz the circuit cannot pass. Okay, the simplest example of low pass filter circuit is our RC filter. Okay, first we will do the passive one. Okay, then we will go for the DC open bass. So for example, I am this type of it. So we are very familiar with this type circuit. Okay, RC. Okay, we are giving RC circuit is there. Okay, so if this one is basically a low pass filter, but how it works we will first look. Okay, so this V output can be simply written as this is a C, capacitor having capacitance C, so the corresponding impedance should be 1 by SC. Okay, so the V output will be simply V in 1 by SC upon R plus 1 by SC. Okay, using the voltage divider rule, we are just applying the basic voltage divider rule. Okay, okay, so this expression, this way is simple network theory. Okay, from simple network theory we can write this one. Now what we are doing, we are writing after solving it should be 1 plus SCR. Okay, SC should be cancelled. V out by V in is 1 by 1 plus SCR. Okay, so if we plot this one is nothing but simply some gain. Okay, gain term, so this gain is 1 by 1 plus SCR. So one more thing we can write, 1 plus, we can write j omega by 1 by RC. Okay, why I am writing, because we can write 1 omega by omega h, where this omega h goes to 1 by RC. Okay, so again this one I am writing here, this V output by V in frequency domain we are writing, so we can write as a 1 plus j omega, omega should be your 2 pi f and 2 pi fh. This 2 pi cancel, so we can write 1 by 1 plus 1 by jfh. Okay, so the final expression for this circuit we can write as V output S by V input. S is nothing but simply 1 by 1 plus J F by Fh, where Fh is nothing but simply what? Fh 1 by 2 pi RC. Okay, if 2 pi Fh, if we make it 2 pi Fh, it should be 1 by RC, and which is nothing but omega H. Okay, so this one is the expression. Okay, so now we can plot this one, this. Okay, so for plotting this one, what we have to do? Basically, wait for 1 minute. Basically, we have this R and C. This one is our V in. Okay, we can write as plus or minus. And this one is a V output. Okay. So after solving, what we get? V output by V in as a 1 by 1 plus J of F by Fh. Okay, so if we take the modulus, okay, it will give 1 by 1 plus F by Fh whole square, because in the numerator 1 plus J0. Okay, so we know the formula for A plus JB equals to square root of A square plus B square. Okay, using that formula we can write 1 by square root of 1 plus Fh. Now we have to plot this one. Okay, to plot this one, what we are doing? This should be your gain. Okay, I am writing dB in frequency. Okay, so case 1, if this one, if there is a situation where this F, there F should be what? This F should be less than Fh. Okay, F should be less than Fh. Okay, means frequency, somehow there is some frequency, say Fh. So if Fh case 1, we can write this one as a case 1. Okay, when F is less than 1, F is less than Fh, so Fh is high, so F by Fh value will be low. Okay, and this should be low value, and a square of low value is also low, very low. You can say low value, very low. So this V naught by V in magnitude will be nearly equals to 1. Okay, because this F by Fh value will be low, so it will keep the almost constant value, that is our 1. Okay, and when case 2, when F equals to Fh, the gain, this G value should be 1 by root 2, 0.707. So it should be, at that point there should be some less value, that is for 0 dB it should be 1. Now for this point it should be 0. Magnitude, okay, so it magnitude it should be minus 3 dB. Okay, then if we go for case 3, where F value is much greater than Fh, if f is much greater than fh, so this value should be high, so the gain should be low. Low value of gain will become, and it will go down. Okay, so this one is the frequency response. So this should be the pass band. Okay, and this should be the stop band. Is it clear? Very simple. Okay, so this one, this circuitry RC is nothing but simply the low pass filter. Okay, so in your op-amp based circuitry, what we have to do, that I will discuss now. So basic is clear. So now again I am taking a new page. Okay, okay, so now we have to go for the, that one is our first order. Okay, first order low pass filter. Okay, again I am just making a small diagram. Okay, so this one is your first order. Order low pass filter. Okay, having the corresponding frequency response. Okay, this would be fh, this would be 0 dB, minus 3 dB. If you magnitude, if you are writing in magnitude, it should be 0.707. okay, this one is your pass band, this would be stop band. Okay, now for op-amp based circuitry. So op-amp, why we are using op-amp? That's why we are telling as a active, because of using op-amp we can tune the frequency as well as gain. So for op-amp based circuitry, if we have to make op-amp based low pass filter, what we have to do, we have to take an op-amp. Okay, this would be your inverting in, non-inverting in. So feedback is in RF, R1, take this one. Okay, so basically what we are doing, we are just putting the, okay, RC. So if we just look this portion only, okay, if we just look this, the V output, and now I am saying this one is V1. So this one is nothing but simply your non-inverting amplifier. Yes or no? Means your simply your this will be the circuit minus first RF, R1 should be grounded. Now I am saying V1. Now we are not making this one. So this one is our, so V output equals to 1 plus RF, R1 into V1. Is it clear from op-amp? Now what I am doing, this RC, so V1 value we can write, V1 value Okay, but I am different. This v1 value, this v1 is nothing but simply yours what, 1 by 1 plus SCR into V in. Okay, V1 V in time 1 by SCR. If we are solving this one, it will give V1. Okay, so now this V1 we know. Okay, now you just put in this expression V out equals to 1 RF by R1 into V1, that is V in by 1 plus SCR. Now we can write this, say AF V in into 1 plus SCR. So V out by V in is simply your sum gain. Okay, so this one is also a first order low pass filter. Why we are telling this a first order? Because the roll off is here minus 20 dB per decade. Okay, so this one is your first order. If it should be second order, it should be minus 40 dB, minus 60 for the third order. So initially there is no gain. The gain is 1. So now there is a controllable gain. So AF. So AF is yours passband gain, and the value is AF value is yours 1 plus RF by R1. Okay, so now next, one plus RF by R1. Okay, now this one is your, what I am saying, this one is your passband gain of the filter. Okay, and F is the input frequency, or simply frequency of input signal. Okay, if we write in terms of F, or okay, again I am writing V output by V in is our AF 1 plus, instead of S you can write J omega CR, or we can write 1 plus J omega, so 2 pi F into 1 by FH, 2 pi FH. Okay, it's omega F, this should be omega, and omega H. Omega H, nothing but simply 1 by RC, or 2 pi FH 1 by RC. So FH should be, okay, so this 2 pi cancel out. So the function value is AF by 1 plus okay. After that, this one is the overall transfer function. Okay, output by input. Okay, if we take the magnitude of this one, V naught by V, you can write the frequency term also, should be AF by square root of 1 plus F by FH square. Okay, this one is the magnitude part. Okay, and the corresponding phase, so it should be minus tan inverse f by fh, yes or no? Because this one is the transfer function we are, okay. So if we are looking for the phase, so a plus j 0, okay. So the phase tan inverse, okay, b by a, so it should be 0. So this should be tan inverse 0 by af by tan inverse f by f. So tan inverse 0 0, so 0 0 minus 10, so it should be, okay. So the page, okay, now I am using different page. So what we observe, that we have a filter like this one, RF R1 RF R1, and this should be a R R and C, and V in and V out, and finally what we got, V out by V in equals to some function a by 1 plus j by f by fh, where a is 1 plus rf by r1, okay, and f is the frequency of the input signal, frequency of input signal, and fx 1 by 2 pi rc, high cutoff frequency, high cutoff frequency, okay, of the filter, of the corresponding filter, okay. So now the corresponding magnitude plot, oh, so the magnitude we can simply write, already it's 1 plus f by fx, and the corresponding phase minus 10 fx. Now if we go for the plot of this one, so if we have to plot this V output by V in magnitude, that is our AF by 1 plus F by Fx whole, okay. So again just think three cases. Case 1, okay, when this frequency is less than fx, okay. This one is your gain, output by input in dB scale, okay, in frequency, okay. So when f is very less than fx, okay, then the v naught by v in is nearly equals to af, because fh is high, so it should be low, and 1 plus low value is nearly 1 square root 1, so it should be a, so it will give some constant value at f equals to fh. It should be some value, that is fh, that is your 1 by root 2, so the corresponding dB term should be minus 3 dB, okay. After that it will drop down. Case 1, case 2, f equals to fx, then the v output by v in is equals to 1 by root 2 times af, that is 0.707 af. Now the case 3 already discussed, when f is greater than fh, so f is greater than fh, so The denominator term will be high, denominator nominator term will be high, so the gain should be low or it will decrease. Okay, so this one is the overall frequency response for the low pass, and this one is your pass band. Okay, the circuit will pass up to this frequency, up to maximum cutoff frequency fh. This should be stop. Okay, so thank you. So in the next class, in the next lecture, we will cover high pass filter and some numerical, okay, on this filter. Okay, so thank you.